Hello and welcome to Section 17. Section 17 looks at two different concepts. In this video we'll be doing the first of those, which is sequential switching. We'll look at example 1. Sequential switching is this idea of we turn a circuit off and we turn a circuit on and then off and then on. So we oscillate between the off and on states, or between two different types of sources. So we could switch back and forth between, say, a voltage source and a current source. So what we're most interested in is, so up here, so this example down here, so we have this circuit, and so the dashed line represents kind of the ideal case, how long it takes to reach what we call steady state. So steady state is going to be this line up here, and that should be a straight line, but I can't draw straight. Yeah, it's a little better. So we get up there, and we just kind of stay there. And once you're in steady state, you can analyze that using all the techniques. So your current divider, voltage divider, node voltage, mesh current, all that stuff applies when we're at steady state. So how quickly do we get to steady state is dictated by that time constant. It takes 5 time constants to be what we consider at steady state. So you can see at 4 time constants, we're like 98% of the way there. At 5 time constants, you're essentially there. And it's decreasing return, so you asymptotically approach that steady state voltage or current. If you have a really slow circuit, which has a very large time constant, so again, time constants are calculated by multiplying R times C, or taking L and dividing it by R, then you'll get this, this lower curve, which looks kind of like a triangle. And so that one is taking a long time to charge up, and then we switch it off before it fully discharges, and you start to get this triangular appearance. So let's look at that with example 1. So this has been partially solved. So you start off with this circuit here. It starts off in this state where this switch has been open, and then when we get to time equals 0, we shut the switch, and then we analyze the response of V. So this is what you would have done in chapter 16. You would find the response up here. So if you did that, you would find that you would get V of t is 10 minus 10e to the negative 10t for t greater than 0. But what's going to happen at 1 second is we're going to reopen the switch, and we're going to reanalyze the circuit. So the circuit is now going to be composed of just this part over here, because the open switch makes all of this other stuff go away. So all of this stuff won't even be in the circuit. So it's just the stuff in that green box there. So let's look at that. So I've redrawn that here. So again, you would, in your homework, you'll have to evaluate the full circuit. You'll get your initial thing, and then you come down here and you're going to analyze this piece. So this is an unforced circuit. This looks like the stuff, I believe, from section 14. So we have source free. There's no sources. So we could write a differential equation. We could put a node up here at V and a node down here at 0. We could write a differential equation and do all of that, but we don't need to because it's a source-free circuit. There's some shortcuts we can take with time constants. We know that we're solving for V, which is across this capacitor here. We know that it's going to take the form V of t equals V particular plus V natural. Because we have no voltage sources or current sources, we know that this particular response is going to go to 0. And V natural, we know is going to take the form AE to the S1T, but because this is not at 0, we actually get a new equation here. And so the equation on the first page is this equation, AE to the S1T minus the delay, or time of delay, however we want to write it. So normally we have AE S1T, and this is the same thing, except normally our delay has been 0, so we just drop it out. But now we have a time of delay, so that we're going to put a 1 in for that. So that's what's going to happen there. So just rewrite that. V of t will be AE to the S1 t minus d. And then our S1, we can find that with our differential equation. So S1 is just negative 1 over tau. Tau for this kind of circuit is RC. So negative 1 over RC. So our resistance is 2 mega. Mega is e to the 6. Our capacitor is 1 micro. Micro is e to the negative 6. And so you can see how these two pieces are going to cancel out. So we will get negative 1 over 2. So negative 1/2 will be S1. So we get V of t is equal to A. So the same thing as before, we always want to find A last. AE, so S1 is negative 1/2 t. We know our delay is 1 second. So we're going to go ahead and put our -1 in here. And now all we have to do is find A. To find A, we need to know what it is. So we want to find V of 1 plus. So again, we're not doing V of 0 plus because we're not switching at 0. We're switching at time equals 1 second. Because it's a capacitor, it's the same thing. Because it's a capacitor, V of 1 plus will be equal to V of 1 minus. So right before the switch, again, because it's a capacitor and we have that dV over dt, the voltage cannot change instantaneously without creating infinite current. So how do we find voltage at 1 minus? Well, that's what this equation up here is for. This is the voltage from 0 to just before 1 second. So I can plug in 1 for this t, and I will solve for V of 1 minus. So that's going to be 10 minus 10 E. So we no longer get to put a nice 0 up here, but it's not that big of a deal. So we're just going to put in a 1. And I mean, you could put in a 0.99 repeating if you really wanted to, but for what we're doing, just put in a 1. And you calculate that, and you will find that it is 6.321 at 4 sig figs. So what does that mean? If we stop and think about it, so we expect overall that this is going to go away. This is our natural response. So we should get to 10 if we reach steady state. Steady state voltage is 10 volts, but we only got to 6.32. That means that we switched before we reached steady state. And if you go back, you're probably going to looking at so our tau looks like about 1 second. So yeah, we're switching really early if we're switching 1 second. So we're like 1 time constant in when we switch this thing. All right, so let's bring this back down. So we now go V of 1 plus is equal to 6.321 equal to AE. So the cool thing that's going to happen is we're going to get negative 1/2, and then we plug in a 1 minus 1. So we still get that 0 over here. So A be 6.321. And so our answer becomes V of t equal to 6.321 E, so negative 1/2 t minus 1 volts for t greater than 1. So don't accidentally put in t greater than 0 there. All right, so that is your answer. If you have any questions, feel free to reach out.